So let us have another lesson in number theory, and I'm sure, and I want to repeat this, it is important to cover some basic ideas from this book. So I'm going to try my best to cover all the important ideas from this book, because that will give us a good start into this really wonderful topic in problem solving. Today I continue with the same chapter that we began a few days ago, and I'll focus on another idea that has been exemplified in this chapter. This one I think can go by the name of case by case analysis, and it is very easily understood by a good example, and let us spend some time in understanding what is the idea. So, for example, the simplest idea here is that all integers are either odd or even. Now, when you talk about the even integers, you are referring to numbers like 0, -2, -4, 2, 4, and so on. Now, as far as the odd numbers are concerned, you have 1, 3, 5, and then -1, -3, and so on. Now, what is very easy, and I'm just going slow on this rather well-known idea, is to understand that these numbers can be represented as 2 times k. And what is k? K is basically belonging to integers. So, for instance, if I take k is equal to 0, I get 0. If I take k equal to 1, I get 2. If I take k is equal to 2, I get 4. And if I take k is equal to -1, then I get -2, and so on. So by taking different values of k, I get all these numbers which are the even numbers. And here these numbers are represented as the counterpart of 2k is 2k plus 1. For example, if I take k equal to 0, I get 1. If I take k is equal to 1, I get 3. And once again, we will write the same thing. That is, k belongs to integers. Now, this representation of the entire set of numbers as 2k and 2k plus 1 is basically creating two cases. It has to be either here or here. Now, this simple idea can be extended to, instead of odd and even, to division by 3. So when you have division by 3, there is a possibility of having a remainder of 0, 1 or 2, and then 3 again gives a remainder of 0, 4 gives a remainder of 1, 5 gives a remainder of 2, 6 gives a remainder of 0, 7 gives a remainder of 1, 8 gives a remainder of 2, and you can also go backwards. So -1, -2, -3, -4, -5, -6. Now, in the previous case, all the integers were divided into two cases. In this case, the integers are divided into 3 cases. Ones that leave a remainder of 0, the numbers which leave a remainder of 1, and the numbers which leave a remainder of 2. Now, these are the 3 cases we have to consider when we are dividing by 3. And just like this, these are represented as 3k plus 1 and 3k plus 2. So these are the only 3 possibilities when you divide by 3. Either you leave a remainder of 0, or you leave a remainder of 1, or you leave a remainder of 2, and these are the 3 cases when you divide by 3. Now, once again, I want you to remember that k is belonging to integers. So, for example, if I take k is equal to 0, I get 0. When I take k is equal to 1, I get 3. When I take k equal to 2, I get 6, and so on. Same thing for here. When I take k is equal to 1, I get 1. Wait a minute, I'm sorry. When I take k equal to 0, I get 1. When I take k is equal to 1, I get 4, and so on. So, with that, there is nothing special about 2 or 3. It can have any division by any number. So just to tell you, what are the cases when you divide, let's say I'm just picking up some random number. Suppose I'm dividing by, okay, 6. So the various cases are those which leave a remainder of 0 when you divide by 6, those which leave a remainder of 1 when you divide by 6, those which leave a remainder of 2 when you divide by 6, those which leave a remainder of 3 when you divide by 6, those which leave a remainder of 4, and those which leave a remainder of 5. Now, notice here that you have 6 cases to consider when you divide by 6. Similarly, if you divide by 100, you will have 100 cases. One interesting thing about this particular choice of division by 6, and it's a very commonly used trick. If you are looking for primes, primes cannot be in this case. They can be in this case. This cannot be in this case. They can be in this case. They cannot be in this case because this is divisible by 2. So it cannot be here. It cannot be here because this is divisible by 3. It cannot be here because this is divisible by 2, and it can be here. So these are the only 2 possible cases for the representation of a prime number. So this is one nice trick. When you are looking for prime numbers, look for numbers which leave a remainder of 1 when divided by 6 or 5 when divided by 6. Anyway, so this was a short run through of the idea of case by case analysis. How does it help to solve problems? So I just pick up some problems from the book. So this is page number 26. So I'm going to state the problem, and maybe, as always, I want you to just try the problem on your own for a few minutes by pausing the video. I'm just going to proceed and solve the problem. So this is page 26 and problem number 17. Okay, so let me just state the problem. The problem says that prove that n cube plus 4n is always divisible by 5 for all n. Now, we will solve this problem by case analysis. When you divide by 5, the only possibility is that either it leaves a remainder of 1 when you divide by 0 when you divide by 5, 1 when you divide by 5, 2 when you divide by 5, 3 when you divide by 5, 4 when you divide by 5. So these are the 5 possible remainders, and we will consider each case here. So if n belongs to this case, that is n leaves a remainder of 0 when you divide by 5, what happens to n cube plus 4n? N cube leaves a remainder of 0 into 0 into 0 because you can multiply the remainders, plus 4 into 0 because once again you can multiply the remainders, and of course you can add the remainders, and this gives 0. That means that n cube plus 4n leaves a remainder of 0 when you divide by 5 if n itself leaves a remainder of 0. But there are 4 other cases where n can lie, and let us consider each case one by one. So the next case is that n belongs to this category, that is the remainder of n when you divide by 5 is 1. What happens to n cube plus 4n? You get 1 cube plus 4 into n, 4 into 1, and remember that this is the rule we learned a few classes ago, and this turns out to be 1 plus 4, which is basically 0. Because we are dividing by 5. So once again the remainder is 0, which means that n cube plus 4n is divisible by 5. Now let's just proceed with the case 3, which is n leaves a remainder of 2 when you divide by 5. So this is then 2 cube plus 4 into 2, which is nothing but 8 plus 8, and this is nothing but 16, but that is, wait a minute, what's the mistake here? I'm sorry, 4 into 2, 8, and this is 8. 8 plus 8, 16. What's the mistake I'm making? I'm sorry. N is a remainder of 2. So 2 cube is 8, plus 4 into 2 is 8, and there's some problem here. What's the mistake I'm making? N leaves a remainder of 2 when you divide by 5. So n cube. Oh, I'm sorry. I'm really sorry. I have made a mistake in writing down the problem. I'm extremely sorry. And this is actually, and that is the problem. I was not doing a mistake. This is actually n raised to 5. I've copied the problem wrongly. I'm sorry. So let me just proceed with n equal to 2 with this. The previous two we can do similarly. So this becomes then 2 raised to 5 plus 4 into 2. This is 32 plus 8, which is 40, which is nothing but 0 when you divide by 5. Okay, so now let me do n is equal to 3. Now there is, I could do n equal to 3 in the standard way. That is 3 raised to 5 plus 4 into 3. So let me just do this slowly. This can be written as 3 square into 3 cube plus 12. But 3 square itself is 4, and this is 4 into 3, 12 plus 12, and this is 4 into 2 plus 2, and this is 8 plus 2, which is nothing but 0. So I have used the remainder rule to my advantage to simplify these big numbers. Now let's do the last case, which is n equal to 4. So for n is equal to 4, the remainder is now 4 raised to 5 plus 4 into 4, right? So this is the remainder when n raised to 5 plus 4n is divided by 5, and n itself is the remainder of 4. So let's see how to simplify this. This should be easy. There are actually, let me do it by the bad way and also the good way. The bad way is, let's just split this up into 4 square into 4 square into 4 plus 4 square. Now 4 square is nothing but 1 into 1 into 4. Please remember, 4 square is 16. So 16 is basically a remainder of 1 when you divide by 5. So 1 into 1 into 4 plus 1, and this is nothing but 4 plus 1, which is the same as 0. 4 plus 1 is 5. We are dividing mod 5. So in all the cases, we've got a remainder of 0. Now let's do this in another way, which is quite standard, and I think it's, if you haven't picked up the trick yet, you must do this quickly. 4 can also be considered as minus 1. So it's minus 1. 4 can also be considered as minus 1 when you're dividing by 5. So this can be written as minus 1 plus minus 1 into minus 1, and this is nothing but minus 1 plus 1, and this is 0. So this is the, this is what I meant when you can do this in a much nicer way. So anyway, this is a great example of case-by-case analysis, a straightforward problem. But before we close the lesson, let's do one more problem, which also shows one standard way of dealing with these kind of problems. So I'm going to state the problem now. This problem is just, I think, one or two problems down the line. Problem 21 on the same page. Problem 21 on the page number, same page number 26. So on this page, problem 21, what it says is, show that 24 divides p square minus 1 if p is greater than 3, strictly greater than 3, and p is prime. Okay, so let's try to do this problem by case analysis. Now, the first simple trick is you have to split this problem into two smaller problems. Instead of worrying about division by 24, the prime factorization of 24 gives me 3 into 8. Now, 3 and 8 are co-prime, so I would rather convert this into two problems. First, I will prove that 3 divides p square minus 1, and I will also prove that 8 divides p square minus 1, provided of course this is true. And then that would conclude that 24 divides p square minus 1 because the GCD of 3 and 8 is 1. So this is the two new problems we have. Let's try to prove 3 divides p square minus 1, and let's also prove that 8 divides p square minus 1. And we'll do this by, at least the first part, we'll do it by case analysis. So let's start. I'm going to prove that 3 divides p square minus 1 given the conditions of the problem, which is p is greater than 1. Now, the only possibilities for p are not 3k, because then it would not be prime. There is a possibility of it being in the class of 3k plus 1 and also in the category of 3k plus 2. So these two possibilities exist if p is prime and greater than 3. If p is prime and greater than 3, it cannot be divisible by 3. But it could be in this category or this category. So let us see what will happen. This is the case 1 and this is case 2. So in the first case, if p leaves a remainder of 1 when you divide by 3, then p square minus 1 leaves a remainder of 1 into 1 minus 1, which is 0. In other words, p square minus 1 is divisible by 3 in this case. But there is also one more case, which is p leaves a remainder of 2 when you divide by 3, in which case p square minus 1 in case 2, p square minus 1 leaves the same remainder of 2 into 2 minus 1, because you can multiply the remainders, and this is nothing but 3, which is nothing but 0. So once again, p square minus 1 is divisible by 3, and we have finished this part of the problem. Our main problem, mind you, is not this. It is to prove that 24 divides p square minus 1 for all primes greater than 3. So we have finished this part. Now let's try this one. 8 divides p square minus 1. So for that, let's try this. Let's try factorizing p squared minus 1. So 8 divides p plus 1 into p minus 1. The factorization of p square minus 1. This is what we have to prove. So here we'll just quickly finish this. If p is greater than 3 and prime, so p must be odd, which means that this is even into even. So p minus 1 is going to be even because p is odd, and p plus 1 is also going to be even. But notice further that these are two consecutive even numbers. These are two consecutive even numbers. Now, if two even numbers are consecutive, one of them is definitely going to be divisible by 4. Both are divisible by 2, but one of them is going to be divisible by 4, either this or this. So, if one of them is divisible by 4 and the other number is divisible by 2, then the whole number is divisible by 4 into 8. And that takes part about this part of the problem, and we have finished solving this problem by case analysis. Now, I'm going to end the lesson with a very short problem. It says that a small extension of this problem. So, this is actually going to be done in a minute. So, let's finish this as well. The problem is exactly the same. It says that prove that 24 divides p square minus q square, where p, q are primes and greater than 3, strictly greater than 3. Now this one we can make short work of this. Just rearrange p square minus q square as p square minus 1 plus, minus q square minus 1, and we just proved that this is divisible by 24. This is also divisible by 24. So both of them, the subtraction of these two is also divisible by 24, and we are done. So we picked up one more important idea in basic number theory, which is case-by-case analysis. Please go through the book. There are lots of problems to make this idea very strong. I expect you to use the book. That's the whole purpose of this series of classes. Very soon we will shift to the next chapter on number theory, and with that we should be reasonably ready with the basics of number theory for our exam. All the best. See you. Bye.